Let's go through the two important messages that we have carried in the last video. Okay, so last video we said that impulse is equal to the area under the net force time graph. So if we have a net force time graph that shows the sudden events, okay, this is the start of the sudden event when it starts to be in contact, then it spikes, then at the end when it starts to break contact, then the force drops back to zero. So this is our net force time graph. Then we know that this area under here will be represented as impulse, because impulse is equal to the area under the force time graph. And if you put it into equation, the impulse represented by the symbol J is now equals to the integration of the net force time graph from time start of the event T1 to the end of the event T2. Okay, but actually in our syllabus, right, we don't really try to talk about integration a lot because our maths is not really there yet. So what we do is we will try to simplify the situation by finding the average for the force. Okay, so the force, there are regions where the force is mild, there are regions where the force is strong, and you have region where the force is mild, right? So what if we find an average to the force? If we find the average to the force, we're able to simplify this graph here to be something like this. Okay, we replace the changing force over here with a single constant force that we call it as the average force. The duration is still the same, it's still the same start, it's still the same end of the event, but we replace the changing force with a constant average force. Okay, what needs to be very important, what needs to be careful about is this area under here, which represent impulse, should still be the same if you find the average for the force. So this area should still be the same as before. So the impulse does not change. What we change is just the changing force. We find an average to it. So if we change it to a rectangle, now this is a very easy area to be found. Okay, the area is just the length multiplied by the width, and since we know the length to be equal to the average force and the width to be equal to the duration, now the equation can be simplified from a complicated integration to just be the average force multiplied by the duration delta t. Okay, the duration delta t is from the start of the event to the end of the event. Now this equation is much more easier, and this is the equation that we'll be using in our syllabus to define impulse. So impulse is the product of the average force multiplied by the duration in which that average force is being exerted. Okay, so that's the first important message. The second important message is impulse momentum theorem. We learned from just now that impulse experienced by an object is equals to the change in momentum that happens to the object. If an object experiences a certain impulse, the object will experience the same amount of change in momentum. Okay, if we expand this equation, the change in momentum is just the momentum final minus the momentum initial. So momentum final is just mass times the final velocity. Momentum initial is just mass multiplied by the initial velocity. Okay, you can also expand the impulse based on what we defined earlier to be the average force multiplied by the duration, and it's equals to final minus initial momentum. Okay, so that is impulse momentum theorem. You can modify in any way you prefer to suit what the question needs. And impulse and momentum, if you want to really define it, you can just define it using the impulse momentum theorem to be the change in momentum. Okay, so impulse is actually a vector quantity, yeah? But all my explanation here has been treating it as a scalar because I've been considering 1D situation only. There's no x and y involved. So if you really have to consider 2D situation, then actually you have to split into component. So the impulse in the x component is equal to the average force in the x component multiplied by the duration. So you have your y component as well. So impulse momentum theorem, you should also analyze it in x component and y component as well. But our syllabus limit ourselves to 1D situation, so it's okay to drop the x and y actually and just do it in this method or this method. Okay, so it's actually a vector quantity, but we can simplify it since our syllabus only asks for 1D situation only. Okay, so impulse is a vector quantity, and the unit for impulse is either kg ms negative 1, which you can derive from the unit for momentum. Momentum mass is kg, velocity is ms negative 1, or you can call it as Newton second because it's force multiplied by time, so Newton multiplied by second. Okay, so this is the end of my explanation for momentum and impulse. There's something I get a bit fuzzy is I sort of a bit brush it off is actually this average force here is actually representing the average for the net force experience. So it's actually net force that we're talking about here. Okay, I don't think it's being mentioned very clearly in a lot of references, but when we talk about impulse, it's actually related to the area under the net force time graph. Okay, so something to be careful of. So in the next video, we'll be talking about a few questions for impulse and momentum.